Okay, so are there any questions from the previous lecture? Okay, if not, let's just. Okay, so last lecture. We saw about Eulerian trails. This time we will see something similar, but slightly different. Okay. So, what is an Eulerian trail? To recall, suppose you're given a simple graph. Right? What is an Eulerian trail?
Visits all
A closed cycle or a circuit that visits every edge of G. Right? Exactly. Now, another complementary notion to this is you're given a graph and you want to visit every vertex exactly once. Right? So, what is a Hamiltonian graph? You say a simple graph G is Hamiltonian. Graph with Hamiltonian cycle. So, what is a Hamiltonian cycle? It is a cycle that visits every vertex of G exactly. So, this is a closed trail visiting every vertex of G exactly once. So, is the definition clear? We will see a couple of examples. So, can someone give me a Hamiltonian cycle in this graph?
1, 2, 4, 3, 1.
This one, right? So, this is a Hamiltonian cycle. So, let's see another example. This one.
Two, 1, 3, 4.
Is that a cycle? So, it's a closed trail. So, what do we want? We want a closed trail visiting every vertex in G exactly once. So, what does that mean? So, you need to walk beginning it at a vertex V and visit every vertex in G and come back to it. Right? That's what a closed trail means.
so 1, 3, 4, 1.
But that does not visit 2, right?
Oh,
So
yes,
what should you
yes,
do? Yeah, you must start at a vertex, you must end at that vertex, and you must visit every vertex in the graph. So if we call this graph G and this graph H, what we get is that what we observe is that G is Hamiltonian, but H is not. Is this clear? If there are any questions, you should ask now. Okay, so although H does not have a Hamiltonian cycle, it definitely has a path that starts at 2, visits every vertex and ends at 4, right? So just like we have the notion of Eulerian trail and Eulerian paths, we have Hamiltonian cycle as well as a Hamiltonian path. So Hamiltonian path is a path from or a sequence of vertices from, let's say, U to V that visits every vertex of G exactly once. So even here I must mention exactly once. Is exactly once. It's every vertex of G. Right? So it might begin at a vertex and it might end at a different vertex. It might not be a cycle, but we might still visit every vertex exactly once. Is that clear?
Yes, ma'am.
Okay. So now we saw a graph. We have some graphs that have Eulerian cycles and some did not have, right? Just as we saw the condition, right? So if and only if every vertex has even degree, the graph will have an Eulerian cycle. So if there is one vertex for odd degree, it might not have an Eulerian. It will not have an Eulerian cycle. But if it has exactly two vertices of odd degree, it will have an Eulerian path. So similar to that, can we get necessary and sufficient conditions for a graph to have a Hamiltonian cycle? That is a question. Now, what is? Can someone see what the connection between Eulerian trails and Hamiltonian cycle is? Like for example, if the graph is Eulerian, can we say that it is Hamiltonian? Is it? Okay. So can you give me a graph? So you're saying that if a graph is Eulerian, then it is also Hamiltonian, or the other
The
way.
first one. If it is Eulerian,
So what do you
then
mean?
it is Hamiltonian.
So what do you mean by that? Let's just write down what he's saying. So when do you say that G is Eulerian? This means that there is
Ma'am, I tried
closed
that.
trail. Okay. But anyway, let's just write. There is a closed trail that visits every edge exactly. And when do you say that G is Hamiltonian? There is a closed trail that visits every vertex exactly. So now let's see some examples. So this should be clear. The definitions of Eulerian trails and Hamiltonian. So now let's see some examples. I will draw 4 examples and then you can take a look at each of them and let me know. Okay. So yeah, let's call this G1. So now you can take some time, like 2-3 minutes, and figure out which ones are Hamiltonian, which ones are Eulerian. Okay, so did you figure out? So is this graph is G1 Eulerian?
Yes.
So this is an Eulerian trail. Is G1 also Hamiltonian? It is, right? The same Eulerian cycle. It's also a Hamiltonian cycle. So this is Eulerian and Hamiltonian. What about G2?
It's only an Eulerian.
Yeah, it is Eulerian because every vertex has even degree, right? So that immediately tells us that the graph is Eulerian. And if you try to figure out if the graph is Hamiltonian, you might try to walk along paths and you will always visit one vertex that you already visited before discovering a new vertex. So this graph is Eulerian, not Hamiltonian. What about this one?
Hamiltonian and not Eulerian.
This is not Eulerian because there is one vertex, not degree. This is not Eulerian. This
Ma'am,
graph
there are
is
two
neither Eulerian.
vertices with odd degree, right? In G3.
Yeah. So what? Right. So what does that mean? That means that there is an Eulerian path in
Yes.
the graph, right? Yeah. But when do you say a graph is Eulerian? If there is an Eulerian curve or an
Oh,
Eulerian
okay,
cycle.
okay.
There is an Eulerian path, that's a weaker thing. You don't say that the
Okay.
graph is Eulerian. We say the graph is Eulerian when the strongest condition is satisfied.
Okay.
So that is true. This graph is not Eulerian, but it has an Eulerian cycle. The same is also true about G4. If you look at it, the graph is not Hamiltonian, but it has an Hamiltonian path, right? This one. The Z is actually a Hamiltonian path. It visits every vertex exactly once. It's just that it cannot come back to the vertex from very start. Right? Okay. So there is no connection between Eulerian. When I mean connection, you cannot expect an Eulerian graph to be Hamiltonian and vice versa. Just as you would have thought about it. You would have expected it to be true, but that's not. Okay. So in the case of Eulerian traits, right, we had a very nice condition to show that this graph has an Eulerian trait. You don't even have to think about it, right? You don't have to try all the paths and then figure out. You just have to check whether every vertex has even degree. Right? How can we do the same thing for Hamiltonian graphs? So you're given a graph G, simple graph, and you want to test whether this graph is Hamiltonian or not. Is there a nice condition that you can use? So surprisingly, we do not know any necessary and sufficient conditions for a graph to be Hamiltonian. But although Eulerian is a very nice property, to test Hamiltonian, so this is named after a mathematician, Hamiltonian. It's not clear how to, is there any property that helps us test whether a graph is Hamiltonian just by looking at the degree or the connected components and so on. We have like very weak connections, weak statements that we'll see one of the weak. It's not a weak statement, but it's not a necessary and sufficient condition. We'll see one statement. So, okay. So so there are two theorems. One was proved by Dirac in 1952 and then Ore in 1960. We will see the later theorem because the first one will become a corollary of this one. So I want to make the proof easy. Better. So let's just see. This is from 1960. So this was not the first theorem. The first one was due to Dirac in 1952, but the proof there is slightly complicated. This is easy, and that just becomes a corollary. So we'll see this. So what is the statement? So Eulerian trails were characterized by just looking at the degree of the vertices. Now can we do the same thing for Hamiltonian graphs? So let's say that G is a simple graph. At least 3 vertices. And if you look at the degree of any two vertices, this degree is at least so all G is 100. Is the statement clear? So if you look at the sum of the pairwise degrees of the vertices, if they exceed the number of vertices, then you can say that the graph is Hamiltonian. That is, there are sufficiently many edges in the graph. That's what we are trying to say. If the graph is like really dense, a lot of edges, then you can somehow ensure the graph is Hamiltonian. Okay. So now let us try a proof together. So G is a simple graph. We want to try the contrapositive. And let us assume that G is non-Hamiltonian. Because I know that there is no cycle in the graph that visits every vertex exactly once. So what can I do to make the graph non-Hamiltonian? Let's say even this one, right? Let's take this one. Or maybe this one. Right, so this we know is a Hamiltonian path. Right? I know that this graph has a Hamiltonian path. Now, suppose I wanted to create a graph that has a Hamiltonian cycle. What should I do to G4?
We can add an extra edge between, like, let's say the top left and the center, one and the center.
This one, right? You can. Or in fact, you can even add an edge between 1 and 4. So that is, if you have a Hamiltonian path in the graph already, then what you can just do is you can add an extra edge from the last vertex of the path to the first vertex of the path, and you will get a Hamiltonian cycle, right? So we know that the graph is not Hamiltonian. Let's keep adding edges, right, and see what happens. We want to say that if the graph is non-Hamiltonian, then you can always find a pair of vertices with insufficient degree. When you sum the degree, it will be much less. Right? Otherwise, if there is enough degree, you will find a Hamiltonian cycle. That's what I want to add. Right? So G is non-Hamiltonian. Let's keep adding extra edges. Add extra edges. Okay. To make G maximally non-Hamiltonian. So what do I mean by that? If you add one more edge to the graph, it will become Hamiltonian. So at that point, you stop. Until then, you keep adding edges. Right? For example, in this, I can add some, let's say this one, for some random, not random edges, some arbitrary edges, so that there are sufficient edges in the graph, but the graph is still not Hamiltonian. You keep adding all these edges. You pump as many edges as possible into the graph. Right? So if you will be left with a new graph, let the new graph be G2. So if you add one more edge to G tilde, then it will become Hamiltonian. Okay. So because you only added extra edges, what can happen is the degree can only increase. We did not remove anything. We are only adding additional edges. Now, we know that suppose xy, right, is not an edge in the graph. And if I add xy to G tilde, then I know that there is a Hamiltonian cycle. Is that clear? Is this statement clear? XY is not an edge.
Ma'am, could you explain it once again?
Okay. So what are we doing? What do we want to prove? We want to say that if the graph is non-Hamiltonian, then you can find a couple of vertices B and W such that if you sum the degree will, the sum of the degrees will be strictly less than n minus 1. So I'm beginning with the graph that is non-Hamiltonian. And this is simple graph. Now what I will do is I will keep adding extra edges to the graph in such a way that if I add one more edge, I will stop at the point where if I add one more edge to the graph, it will become Hamiltonian. So that is what I mean by maximally non-Hamiltonian. Addition of one more edge to the graph, it is maximal in that sense. You cannot add any more edge and still ensure that the graph is non-Hamiltonian. In that new graph, that we call it G tilde. So what is a property that G tilde has? So the degree of every vertex in G tilde will only be larger than the degree of vertices in G because we only added edge. And if xy, there is some edge that is not in G, and you added it to G tilde, definitely there is a Hamiltonian cycle because G tilde is maximally non-Hamiltonian. Right? That in one more edge, the graph will become. Is it clear now? I can repeat it again. It's not clear. Yeah, you should ask questions.
Yes, ma'am. It's fine.
So what do we know about G tilde from this property? From this fact, right? If I add xy to G tilde, then there is a Hamiltonian cycle. There is some property that you can extract out of this. What is true in G tilde? So let's say there are n vertices, right? That's what we said. It has n vertices. So let's call these vertices B1, V2, V3, V10. Let's take X is V1 and Y is V2. What can you say about the edges? This is in G.
Ma'am, we can have a complete graph from V1 to Vn minus 1 and then connect Vn to just one node, and we'll have a graph with which doesn't have which isn't a Hamiltonian graph, but will become one if you add another edge.
Okay, so what you're saying is we can just remove one edge of sorts. Like we can make the graph maximally like complete graph, and then one portion alone you'll remove so that it is not Hamiltonian.
Yes.
But it depends on what graph you are given, right? For example, if the graph given is just this one, let's say. Just editing this, which I shouldn't do, but this graph is not Hamiltonian, and I can just add one edge here, which is this edge, and make the graph Hamiltonian, right? But it's not like near complete or anything. So you don't know what the graph G is. That is important. You don't know anything about the graph G. The only thing you know is it has at least 3 vertices and it's a simple graph. This should not be like really difficult. I mean, the question that I'm asking, what is it that we know about the edge relationship between these vertices? If you're unable to answer this, then we have to like revisit the.
There is
So
a
we have,
Hamiltonian path.
so does this exist in the graph? Okay, it should not be directed. It's not there. Is this clear that this exists in the graph?
Yes.
Right? You can, there is a Hamiltonian. So if you add xy, then there will be a Hamiltonian cycle. So if you remove xy, there should be a Hamiltonian path, right? There was a question.
Is it a Hamiltonian walk?
So what is this Hamiltonian walk? What do you mean?
Walk and okay, Hamiltonian path. Okay, if you're written, then there is a Hamiltonian cycle in G.
Okay.
G tilde.
Yes. So if xy is, so what is G? Right? G is the original graph that is given. Now G tilde is the graph where you add as many edges as possible to G in such a way that if you add one more edge, the graph will have a Hamiltonian cycle. Okay? So if xy is not an edge in G, and if you add xy to the edge set of G tilde, then you will find a Hamiltonian cycle in G tilde. That is how the graph G tilde is constructed.
Ma'am, but xy is not in EG tilde, right? I mean, if we add xy to EG tilde, then that
Correct,
becomes.
correct. So G tilde is a graph. Okay, so what do I mean? What have I written here? Let me write it. So G tilde is a graph, is a new graph.
G tilde is non-Hamiltonian, right?
Yes, G
Okay.
tilde is a new graph that has the property that. So now let me edit whatever I've written. Yes, xy is not in G tilde. That is it. But what is the property for any xy that is in the edge set of G? If xy is added to the edge set of G tilde, that's what I mean by if xy. Or let me just write in English. Let me not put in. If xy is added to E of G tilde, then what can you say?
Then EG tilde would have a Hamiltonian cycle.
So then there is a Hamiltonian cycle in G. Is this clear?
Yes, ma'am. Now it's clear.
Right? Okay. So maybe I should have written English. Okay. So what does this mean? You can order the vertices of G tilde such that there is a path from X to Y, right? Beginning at X, ending at Y, and every other vertex is visited in between. So if I add this, I'll get a Hamiltonian cycle. Right? Okay. So now what do we want to show? We want to show that there exists a pair of vertices. Whose sum is very low. The degree of sum of the degrees is very low. Now, let's try to see. Now, suppose there are two vertices here. Let me call this vi and vi minus 1. Okay. Suppose there is an edge from v1 to vi and an edge from vi plus I minus 1 to vn. Then what can you say? Let me write in English for you. Suppose v1 vi minus 1 is in the edge set of G tilde and v1 and v, yeah, sorry. Vi minus 1 vn. What can be said about the graph G tilde?
Then there exists a Hamiltonian cycle, namely from x to vi to vi plus 1 dot 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 all the way to vx, and then to vi minus 1 to vi minus 2 dot 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 to v1. That is x. Yes.
So what he's saying is, sorry, yeah, you should have done. So you traverse from here. No, it should not be like that. Sorry. You go this way, go this way. Is that clear? I hope you can see the retracing. I don't know how to do it. You can try this color. So you go this way, you go here, you come back to the line. Is that clear? So then G tilde has a Hamiltonian cycle. Right? V1 to Vi minus 1, Vn to Vi to V1. Is this clear?
Yes,
So what
ma'am.
can we say about these two edges? If both of them are there, then there is a Hamiltonian cycle in G tilde. But what do we know about G tilde?
It is non-Hamiltonian.
Right.
So
G tilde is,
such a situation is not possible.
so what situation is not possible? That should be clear, right? G tilde is Hamiltonian, non-Hamiltonian, so there cannot be a Hamiltonian cycle. So what can we say about this graph from this statement? Can this edge and this edge be in the graph?
No.
No, right? So for every I 2 to n, exactly one or at most one. At most one of vi, v1, vi, and vi minus 1 vn is in G tilde, right? Else there will be a Hamiltonian cycle. So what can you say now about the degree of x and degree of y? So for every edge that is there, for every edge incident on x, there is one edge that is cannot be incident on y, right? So if you count 1 degree here, you cannot count this degree here. If you count, if v1, v3 is there, definitely v2, vn cannot be there. If v1, v4 is there, v3, vn cannot be there. So what can be the sum of the degrees?
At most n minus 1.
Plus n minus 1, right? So now one thing to note is this is the degree of x in G tilde. So okay, so whenever we write degree of a vertex and so moving forward, you will see lots of graphs that will play around with lots of graphs, like G1, G2, G3, and so on. And we might talk about degree of vertex being in G1 and then in G2 and so on. So we will denote the subscript, denote the graph by the subscript. So the degree of vertex P in the graph G. So here what I mean is the degree of x in G tilde plus the degree of y in G tilde is at most n minus 1. So what can you say about their degrees in G?
Again, at most n minus 1 because we've just been adding what edges.
Right, exactly. So what did we do to get G tilde from G? we always added extra edges. So the degree will only increase. So the degree of x in G plus the degree of y in G is again almost n minus 1. Right? So which is a contradiction. This means that if this condition is true for every pair of vertices, then the graph has to be Hamiltonian. So any questions so far? Was the proof clear?
Ma'am?
Huh.
Ma'am, could you scroll up for a minute?
Mhm.
Yeah, over here in red, you've written G tilde as a new graph that has a property that XY belongs to EG.
Mhm.
The XY doesn't belong to EG and XY belongs to EG tilde.
Did I mess up? So, oh, yeah, probably that's true. Right. So we have a graph G, and I want to construct a new graph. I know that G is non-Hamiltonian for every xy that's not in the H. I add it to the H, H set of G tilde, and try to make it maximally non-Hamiltonian. That's it. My bad.
Yeah, okay.
I think initially it was written correctly, probably. I'm not sure. When it turned to English, maybe I just messed up. Yeah, sorry. So, yeah, is everything else clear? I mean, after this edit is done, I hope things are clear.
Yes, ma'am.
Okay. So now, Dirac's theorem was actually proved before Ore's theorem in 1952, but it's just a corollary of Ore's theorem. So I'm just going to state simple graph with at least 3 vertices. And if the degree of every vertex is greater than n by 2, then G is Hamiltonian. So this is just a corollary of the previous theorem by averaging arguments. But if you, yeah, if there is a vertex of degree less than n by 2, then it is. Okay, so this is one way to show that the graph is Hamiltonian. That is, if this is true, then the graph is Hamiltonian. But unfortunately, we do not know any necessary and sufficient conditions for the graph to be Hamiltonian. Okay? So this whole thing that we saw so far, the discussion is about undirected graphs. Okay? So we should also talk about directed graphs. So I will just write down the statement for directed graphs, and it will be an exercise. Okay? Just as this was an exercise for Euler. Yeah, this one, right? The same. So this will also be your homework. This one. So here is the statement for digraphs. So what do you expect? So let's just look at Dirac's theorem and see what would be a possible statement for directed graphs. So G is a strongly connected. Then if the in degree, because we have like directed graphs, there is in degree and out degree. Then G is not. Okay, so this is a statement for directed graphs. There are several new results now that have come up later on in the 70s. They talked about what is a condition for a graph to have a Hamiltonian path and so on. And these proofs also follow similar. Might not be exactly the same, but this is one demonstration. But so far, we do not know of any condition that is both necessary and sufficient for a graph to have a Hamiltonian cycle. Just like we have this in the case of Eulerian trails, but unfortunately for Hamiltonian cycles, we do not have. So I want to talk about one thing before finishing this part. So now, although this is true for general directed graphs, There are some special kinds of directed graphs that we saw in the first lecture called tournaments. These tournaments have several nice properties, and one of them is about Hamiltonicity, the graphs. So what is a tournament? So we saw this picture, right, where you had players who played against each other, and then the match sort of was an elimination challenge. Right? At every stage, the person who lost the match was eliminated, like a league, right? An elimination tournament. So such a tournament can actually be represented by a complete graph. Let's say you have a tournament and there are n players in the tournament. So we know that this can be represented by a graph just by labeling them as vertices for a 5 players. And in a tournament, generally every player plays against every other player, right? So one plays against 2, against 3, 4, 5, and so on. And some matches he may win, some matches he will not win. Right? So every player encounters every other player, and it's only once. And let's assume that there are no draws. Right? So when we draw an edge from one player to the other player, if this player wins over the other player, so 1 wins over 2, 2 wins over 5. But it could be that 5 wins over 4. So this is a complete graph. I have to draw some more edges. Yeah, let's just you please draw them if you find any missing edges. So it's a complete graph, and it's also directed. That is, you look at the complete graph and you add an orientation for every edge in the complete graph. The corresponding graph that you get is called a tournament. Now the question is, does every tournament have a Hamiltonian cycle? Or is every tournament Hamiltonian?
Not necessarily. We can just take an edge from I to j if I less than j.
Okay, so he's saying, let me put 4 of them. What do you want to do?
If I is less than j, then I make an edge from I to j. So since in any cycle, the value will be increasing, you will not necessarily find a Hamiltonian cycle. You will not even find a cycle.
All right. But does it have a Hamiltonian path?
Yes.
Do you think that so this is an example, right, of whatever he's saying? This is a
I think
tournament, but it does not have.
every tournament has a Hamiltonian path.
So now the next question is yes. It's the question. Let's try to prove this. So, yeah, for now it's yes, no, but yeah, it's not clear, right? We have not proven it yet, but apparently every tournament does have a Hamiltonian path. Right? So how do you think we should prove this? If there's just one vertex, then there is a Hamiltonian path. There's nothing to prove, right? So for n equal to 1, the statement is true. Right? So let's consider a graph that has n plus 1 vertices or k plus 1 vertices. We're going to do this by induction. So let me just put n plus 1 vertices for convenience. And you have a graph. So there are like some vertices here. So there's some additional bunch of vertices here. Now, let us assume for the purpose of induction, so what is the inductive hypothesis? That any tournament on n vertices has a Hamiltonian. Right? So now, to get from this graph on n vertices to be able to use the induction hypothesis, what am I supposed to do? What do you think we should do? So here is a graph on n plus 1 vertices, and I know that any graph on n vertices has a Hamiltonian path, and I want to use it.
Just start with the Hamiltonian path on n vertices and then try to add a new vertex.
But how do you know that you will get the graph that we started with?
What do you mean?
I mean, so you are given a graph with n plus 1 vertices and you have to go to inductive hypothesis. So what should you do?
Just randomly, like just pick a vertex and exclude it and do the inductive
Exactly,
hypothesis
right?
on the
Yeah,
rest.
So you don't build from the inductive hypothesis, what I'm saying. You have to get to an instance of the inductive hypothesis, right? So you have to, exactly what he said, you have to remove a vertex. Is that clear? Yeah, what he said is right. So let's just look at G minus the vertex V. So when I mean remove a vertex, you have to remove the vertex and all its incident edges. So whenever you read this phrase, right, remove the vertex V, you don't just remove the vertex alone. There'll be dangling edges. So you have to remove all the incident edges that come with the vertex. So what can you say about G minus V? Can you apply the inductive hypothesis? That is also what right? Because you only remove everything else that remains will also be a complete graph with orientations for every edge. So it's a tournament on n vertices. And I know that it has a Hamiltonian path. So this has, let's call this path P. Right? So this path will have a set of vertices. V1 will be a sequence of vertices. V1, V2, V3, so on to Vn. Right? There are n vertices in G minus V.
Ma'am,
So
V is any vertex?
yes, yes. Pick any vertex V.
Okay, ma'am.
You can exclude any vertex. We don't care. So you must remember there is this is more like a complete graphic orientation, right? So it really does not matter which vertex. We will see that. We'll actually see that the choice of the vertex does not matter. So you know that there is a Hamiltonian path. It begins at a vertex and ends at a vertex. Now I want to use this Hamiltonian path to construct a Hamiltonian path in the original graph that also has the vertex. Right? So let's look at how this works. So it's a Hamiltonian path. So you will have V1. There is V2. 3, and so on. Right? And then in G, you have this vertex. Now it's a complete graph with orientations. So these edges, so these edges are also there in G. Right? All these edges will be there. There is no edge that is missed because it's a complete graph. But you do not know the orientation of these edges. That is a problem. You know that there is a Hamiltonian path E that you can use, but you don't know the orientation. Right? Suppose, let's say this was the case. Suppose this was directed this way, and this was directed this way, and everything else somewhat. That is, let's put it this way. That is B to V1 is there. Right? Then what can you say?
And just start the path from V and go to V1 and then V to V1.
You can just do this, right? This is a Hamiltonian cycle. This is a Hamiltonian cycle. Right? So if this exists in the graph, then you're done. Okay, so actually even so if V1 is in E G, then done. V1 so on to Vn is the Hamiltonian path. Now suppose, let me just delete off this one. These orientations we don't. We just know that edges exist. Suppose Vn to V is there. But these things you don't know. These things we don't know. We just know that there is an edge from Vn to V1. Then what can you say? Even then you can actually construct, right? This one is a Hamiltonian path. So now the only case that remains is V to V1 and Vn to V1 are not there. Right? So what do we mean by that? We mean that it's in a different direction. That is, it's like this, and this one is moving away. And in between, edges exist, but you just don't know their directions. Now, what can you do?
If there is for any I, if vi, if the edge vi points towards v, and then v points towards vi plus 1, even then we have a Hamiltonian path.
Right? Okay. So what he says, is it clear to everybody? So if, let's say, I just added the yellow. So let's say V2 is like this. Is yellow visible actually? There is orange. So suppose V2 to V is an edge. V3 to V is also pointing downwards. But let's say that you have V4 and this edge, and that way points upwards. Okay. So then what can you do to construct a Hamiltonian path? You keep going this way. Now you can come down and then go up and then traverse. Is it clear? So the moment this downward arrow flips to an upward arrow, you can use that vertex BI to construct a Hamiltonian path. You come in and then go up. And definitely there should be such a flip, right? From the downward arrow, at some point it has to flip. Probably it flips here only at V2, or it might flip at Vn minus 1. Right? So in case 3, so we know that there exists an I in 1 to n minus 1 such that Vi to V and V to Vi plus 1 are etc. Then you get the Hamiltonian path. V1, you keep going up to Vi this way, and then come down to V, and then move to Vi plus 1, and then continue using the inductive Hamiltonian. So is this clear? The argument? So every tournament might not have a Hamiltonian cycle, but every tournament has a Hamiltonian path. So there are some special graphs that have these nice properties, and it's good to know. Are there any questions? We took a lot of time. Okay, so there is one exercise that I want to give and probably end there.
Why will there always be a flip? Like
so one of them is pointing downwards and the other is pointing upwards. So it should flip at some point, right? If at all. If everything points downwards, then you're in good shape. V1 to Vn minus 1 will come down and move to Vn. Or if everything else points in upward, then V1, V2, V, and then you can do this, right?
Okay. Yes.
Right, at some point this flip has to happen. It could be that in the worst case, this flip happens only at Vn, or in the best case at V1. But definitely there should be such a flip. Is this clear?
Yes.
Okay. So now there is one application that we saw that can be rephrased in this Hamiltonian language. Does anyone see it? In the first lecture, I was motivating you with this Eulerian parts, the bridges of Königsberg. So the bridges of Königsberg problem, which had nothing to do with graphs, right? When you just looked at the question, you were given a map and you're asked whether this is true. And the entire question can actually be rephrased in a graph theoretic sense. Right? And then asked whether the graph is Eulerian. And we saw that that graph is not Eulerian. So there was a similar application that we saw that can be entirely rephrased in the language of Hamiltonian cycles. Let's see if anybody recalls it.
I'm not sure if this was the one, but I think the question was that we just need to show that like in a tournament there is a chain of, you can order them in like by one person is beaten the other person. So like that there is like a chain like that.
There's a winning path.
Yeah, yeah, pretty much there's a Hamiltonian path, yeah.
But there is one more application. Let's see. It's something related to a tour. One entity visiting every square and then coming back.
This is the next one, yeah.
Yeah. So what's the question there? You're given a chessboard, an n cross n chessboard. Let's say it's a 3 cross 3 chessboard. Please imagine these to be squares, approximately squares. So you're given an n cross n chessboard, and you want to ask whether there can be a knight that visits every square on this chessboard legally, and then comes back to the place where it visited. Right? That was what is called a knight's tour. So now the question is, does there exist a knight's tour on an n cross n chessboard for every n? Can you always do this? Like no matter what the dimension of the chessboard is, can you always do this? So these are your vertices. These are the squares you have to visit, right? You have to visit every square. So you should put a vertex corresponding to every square. And what is the order in which you can visit? So let's call this 1, 2, 3, 5, 6, 7. So from 1, where can you go? Where is the knight allowed to go? It can go to 4 and it can go to 8. Right? And from 8, it can go to 3. That's the only possibility. From 4, it can go to 7. From 9, it can go to 6. Right, so this graph that is obtained from the chessboard is called a knight's graph. Now the question is, if you look at the knight's graph on n vertices, does it always have a Hamiltonian cycle? And for what values of n does it have? So this is a homework. Think about it. Does a 3 cross 3 knight's graph have a Hamiltonian cycle? Right? What can you say if it's an n, if n is even, if n is odd, and so on? And how many edges does the knight's graph have? How do you count that? So that's a counting question. And can you show that the knight's graph has some property that we saw earlier in the lecture? What properties did we see earlier that the knight's graph satisfies?
Ma'am, in this knight graph, are you considering the center vertex in the 3x3?
Yes, you have to visit, right? You are supposed to visit the center vertex, but can you always visit?
No.
Yeah, so a 3 cross 3 chessboard does not have a knight's tour, right? Just because of the fact that this vertex has degree 0.
Yeah.
I mean, not degree 0. You can never visit this vertex, right? There are no edges inside. I mean, incident one. So, yeah, so 3 cross 3 is not true. What can you say about 4 cross 4? Oh, okay, so this is answer. So I will change the dimension. I will put 3 cross 4 or something. 3 cross 4. I didn't realize that it was there. So yeah, these questions I'll probably leave it. So there are many questions or many applications that you might not think that they could be rephrased in terms of graphs. But the moment you rephrase this term, so you just abstract out the notion and then rephrase, describe this problem in the language of graph theory, and even with simple terminologies from graph theory, simple statements, you can actually solve these problems. Okay, there are many such problems that we will see later on also, maybe in the next series of lectures. Now we will do combinatorics again, but after some time, maybe next month, we'll again see several problems, which you might not think in terms of graphs, but the moment you turn them into graphs, you'll have like really cool solutions. So you can actually code these things. You can go ahead and take a look at it. So knight's tour, there are programs that run doing this. This is very good, right? So these things have real applications. When you have flights that connect various places, right? Which is the most efficient way to connect these places. You want to like visit all the cities and then come back. You want to plan a tour. So these things are actually applied in, for example, if you go to a tour plan, how do they plan this, right? The most efficient way. So as you go ahead, maybe in your masters, you'll come across problems where these edges have weights. So to go from one city to another city, you have to spend a certain amount of money, right? So there might be a shortest way in which you can visit all these cities and come back to your home. You might want to take the cheapest route, not the most expensive route. So these things are actually very well studied. And these things you will see in algorithms courses. But this is just a starting point for those things. Okay, so this is what with this we will end this module on graph theory. But there will be some more, like some serious amount of graph theory we'll do maybe after a couple of weeks. For now, you will continue combinatorics today and the next couple of lectures. So I'll stop here and Partha will continue. I'm so sorry. I think I overshot. I promised I will finish it in like 35 minutes or something. I'm very sorry. Yeah, I'm so sorry. I think I just misjudged the time.
No problem. I just set up. Give me some time.
Sure. Should I make co-host?
Actually, forgot it.
No, I don't think I have to do anything, but I'll just continue with the recording.
Okay, thanks. Can you hear me clearly, or is it too low? The voice is it clear?
Yes, so it's clear.
Okay. So this graph theory lectures are nice, and we'll again come back to graph theory. Actually, these two are interlinked. There is not much difference between combinatorics and graph theory. It goes side by side. So, and you will see that we will solve problems in combinatorics using graphs and problem in graph theory using combinatorics. So today I am going to introduce another new technique in combinatorics that's more like an analytic technique, like calculus type. And that's called combinatorics via generating functions. So this is relatively simple. And this main idea is, I think all of us have encountered in some sense generating function or techniques around it sometime in our 10+2. This is just advancing that a little bit more. But this is a very powerful technique, although it looks very simple. Any complicated problem has efficient solution using generating function. So the idea is that you have a sequence of numbers, all real numbers for us. Let's say this is n greater than or equal to 0. With this sequence, we really associate a formal power series. So let's say ax and x power n. So x is just an indeterminate variable. So one just comment, it's not relevant for this study, but since I encountered it in my past teaching experience, so some of you may be learning analysis and convergence. So those things has nothing to do here. This is a formal treatment of power series. So this convergence, all these things are not at all issue here. It's a formal treatment. Okay, so this is just a univariate series that infinite series that I associate with these numbers by just throwing an in front of x power n, right? This is meaningfully defined. And one of the reasons that generating functions were used, by the way, the branch of combinatorics where generating function is studied, sometimes broadly called analytic combinatorics. Okay, so I think this was initially introduced to study recurrences. What are recurrences? I mean, we mostly know, like expressing that nth solution with respect to the earlier solutions in a algebraic form. So let's take an example. Maybe there are lots of examples in the textbook. Let's take any example. Let's take a simple example. and your goal is to compute A. There could be multiple ways to solve these recurrences by just your creativity, by looking at it, guess, and there are many ways. And the generating function is one of the systematic ways to solve such problems. I just make two comments. The generating function has its own advantage and disadvantage. Advantage is that it is less error prone. You are more confident of your answer. The disadvantage is that sometimes it could be time consuming than a smart solution. Okay, so this is more like a systematic way to attack the problem, which could be time consuming, but chance that you will make. For example, if you think about this bijective argument kind of more tricky way of looking at combinatorics, you can go wrong very easily if your idea is not correct. This is a big advantage in generating function, that you approach it systematically, not like an ad hoc thing. So you work more, but you are more confident that your solution is correct. And if it is not correct, you will, in analyzing it, you will somewhere, and I mean, most likely you will understand that, oh, I'm doing something wrong. So let's step back and think it again. So these are advantages we have. Okay, so this is a pretty simple example. So how do I solve it? Just from our 10 plus to intuition, I just multiply both sides by x power n plus 1 and write it. Today I have very less time, so I won't go into much details. I just multiply, and since I have an n, I just match it with x power n, because I know intuitively that x power n is going to sit with along with an. Right? So there is no big theory in the generating function. It is all your ideas and manipulation and get the correct results in combinatorics. Okay, so let's just sum over both sides. N greater than or equal to 0. We are doing same thing both the sides, so there is no problem. So look at the left hand side. So if you expand, it starts from a1 x plus a2 x squared and so on. Right? So this term is really like this. Ax is the complete sum starting from n equal to 0. Since it starts from n equal to 1, so this is essentially ax minus az. And then you have 4x, and this term is precisely ax. Right? And this term is, you can take x common, and then it is 1 plus x squared, that infinite series, that geometric series. Right? So let's write it 4x ax minus. And this we know that from our 10 plus 2, this is just 1 by 1 minus x. See here, I don't care about this convergence, mod x less than 1, all these issues, because this is a formal analysis.
Sir, still, even in formal analysis, we should care about that. If there should be some domain of convergence, which is like
you may assume, but you may assume that whatever domain of convergence you want to,
like, it should not be finitely many points. Like,
but it does not matter for our analysis, because we are doing a syntactic analysis. If you want, you can associate a domain of convergence. But because the point is that x has no meaning, I will not substitute x by some value. It's an indeterminate treatment for this.
Yeah, but even for like a totally axiomatic treatment of this formal power series, we will have to, like, same thing should apply for x in some real domain or complex domain.
If you want, you can assume the proper domain of convergence.
Okay. And once that is, if some domain of convergence is there, where this formula is satisfied by our known real number or complex number, then then axiomatically also it is true that the formal power series will be equal to this, right?
Right.
So,
right.
Okay.
But as you see that we will not bother about those things. Those things, if you want, you can think, but those things has no use in the.
No, I mean, like, I can just say that 1 plus x squared equal to x.
Yeah,
So that's right.
Yeah, at the beginning I made it like an explicit. You may think, you may not think, doesn't matter for our life, for this class. Yeah, this is not really an analysis class. Okay,
Sir?
so yes.
So what exactly do you mean by formal analysis?
This is the ring of formal power series. Now, since you are pulling me into that, so this is a ring. So you have not studied that. So this is a ring of formal power series that you can collect all the power series and do derivative on it. You can do calculus on it. You can multiply them. You can add them, subtract them.
Okay.
So, you will see it's not a big issue. I think I know sometimes it comes to mind because you are side by side doing analysis, right? But the analysis class, you'll be more bothered when the series converges, right? What is the range of value for which some series converges? We will not deal with this kind of questions. We are dealing it like a formal identity, like 1 plus x squared up to infinity is a formal identity wise. It is 1 by 1 minus x.
Yes, sir. No, that's what I didn't understand. Like, what do you mean by formal identity?
Okay, so if this if you take, I don't know that you studied ring, so if R is a ring, you can define like this notation means set of all infinite power series over x. Okay, and in this ring you can have, you can also define inverses for some points. For example, like I know that 1 plus x square up to infinity is this thing. So 1 minus x power inverse is these values, this series. Yeah, I don't want to go too much into this thing because it will then drag me into completely different thing, and it will not be any helpful for you at the moment.
Yeah, yes, sir. Yeah.
It's nothing to do with the combinatorics. So you will see that my treatment will be x is as a formal variable, not like some evaluating it even some domain of definition kind of thing. And when solving this kind of equations, you will be often given some initial value. For example, your initial value could be some a0, a1. These things will be provided by you when you analyze the recurrence. For example, that a0 will be, let's say here, assume to be 50 for this example. Okay, so let me just, since these things are not relevant for us, let me just erase these things. Let's try to rearrange whatever we have written here. Because what is my goal? My goal is to get the information about that function ax. Right? So this will be a0 minus 100 x minus 1. And then my ax is a0 minus 4x. It's 100 by x. Yeah, this is just our 10 plus 2 manipulation. Let's continue writing it. And whenever you have this kind of term, the basic idea to use is partial fraction. So I'll just write this x like 1 minus x minus 1 minus 4x. But then I count 3, so I divide it by 3. So that gives me a0 minus 4x. By 3. So this is a nice close form I have. Now see why I said you that it does not matter. All these convergence issues will not come in the class. Now, what is my goal? I want to get the coefficient an that is sitting with the in front of x power n, right? So now I know that ax equal to summation of an x power n. Now, how do you get the coefficient of x power n from this side?
We expand the series.
Just the expand, yes. So this is minus 1, minus 3. So that means an is equal to a0. This is 4 power n minus 100 by 3, 4 power n minus 1. This I did it correctly. This is 50.
So can you explain this step again?
This partial fraction decomposition.
No, so after that you said it
So
equals
I
this.
just wrote it like a infinite binomial series by raising it power minus 1, and you use this identity like 1 minus summation of y power n.
Like the opposite of 1 plus x plus x2.
Sorry?
Like the opposite of the previous summation we used before.
Opposite of the previous summation.
As in you said 1 plus x plus x squared is equal to 1 by 1 minus x.
This is what I wrote here. Is this what you are saying? What is wrote in the left?
Yes, it's okay. Thank you.
This is correct, right?
Yes.
This is power minus 1. Is it clear now? Your doubt, whoever asked.
Yes, it's fine. I understood. Thank you.
It's really simple. So I just leave one exercise. Maybe solve there. There could be multiple this kind of problems where you will be asked to find this closed form of this sequence given the recurrence. So the basic idea, did you get? Is there any doubt? Like, this is a very basic question. You will be given a recurrence and you will be asked to find a value for that sequence an. And this generating function offers you a great tool to do that.
Sir, one can express any linear recurrence in the form of a matrix also, right?
Come. You are jumping ahead to the advanced topic. We will come to all these things. So I'm just starting the generating function. Yes, all these things will come. This matrix form.
I just mean the characteristic function here and also the
right.
characteristic polynomial there matches. Why is so is there any connection?
In fact, it will come. All these things you are saying, it will be later part. So we are just building up on our very basic examples. Okay. So let's look at a product rule. Which is very useful. So often you will be given two sequences. And there will be generating function associated with them. At the moment, our study looks very abstract, but when you work with the real life problems, then you will see why these things are important. And you will be interested to study the product of these two generating functions. This situation will come many times. You have two different sequences and you would like to view the product of their generating functions. And as you can see, the product of the generating function has a very simple formula as its coefficient. So let's see what is the value of Cn. It's really simple, right? Cn is you take x power I from A side, that gives you AI, and then take x power n minus I from B side, that gives you Bn minus I equal to 0 to n. So this is the relation between the coefficients of A, B, and C. This very simple formula is very useful. So I just write like this. I don't have time left today, so let's take one example. You will one can ask several questions. Always your basic principle will be you somehow take your algebraic question or combinatorics question to a question on this formal identities, where you can use binomial theorem to have some closed sum, or multinomial theorem, or some trick from calculus to solve this problem in a systematic way. So let's take an example. Let's take a semester as in this. HOD decides that first K days will be for math, and rest n minus K days will be for physics. And in the first 3 days, one day will be decided as holiday, and the rest, the n minus K days, 2 days will be decided as holidays. So question, what is AN? So AN is the number of ways to do this. This arrangement can happen. That means, so this is a problem description is given in front of you. So semester has exactly n days. For some value of K, the department will decide that, okay, we'll study math for the first K days, and the rest n minus K days will study physics. K could be anything. And then among the days where we are studying math, there will be 1 day leave, holiday. And in the days we are studying physics, there will be 2 days leave. Yeah. So how many ways this arrangement can be made? So obviously K can be anything. So that's the idea. So and second question is, what is the generating function? Generating function for such a sequence. That means there are two questions. Find a combinatorial expression for an and then convert it to a generating function. Is the problem is clear? You will see the example what we are doing. So what is an? In the first K days, you can choose holidays in K choose 1 OS. And in the next n minus K days, you can choose holidays in n minus K choose 2. And K should start from at least 1, right? Because we want to give at least one holiday. So K should start from 1. And K
So it
should
would go up to n minus 2, right?
Right, exactly. It could go up to n minus 2. So this is a kind of a binomial expression form. This you will see how you can simplify and construct the generating function out of it. It's not difficult. So we'll use again these identities. So this is x power j. Now let's derive both the side with the formal variable x. So if you derive the LHS, what we will get? Square. And RHS if you derive, right? So then you know that x by 1 minus x squared is basically, I can just write k times x power k greater than equal to 1. So this is k, and I got an hold of a generating function where k comes in front of the coefficient x power k. So let's call this generating function bx x by 1 minus x squared. Okay, and now I want to get hold of this like a coefficient of another generating function. So my plan is to use some kind of a product rule. You will soon see why. So again, I will play with this identity. And let's derive this twice. So in fact, let's look at this identity. So let's again derive it. So if I derive it, so I'm just doing some simple manipulation. So 1 minus x cubed equal to j greater than equal to 2, j minus 1 x power j minus 2. Now multiply both sides by x squared. What you get? So this, let me just write this as j choose 2. x power j. So this is same as just by mistake I wrote it j. I can just change it to m. So I got another generating function. Let's call it cx, such that cx equal to x squared by 1 over x. Right? Now notice that my an is like kth term coming from the px, and this n minus k by 2 is coming from the cx. So the generating function that I am looking for is, I guess you can guess it now, that ax has this compact form px times bx times cx. So I set up two. What is the idea? So I first found a combinatorial expression for an, and looking at that, I created by some manipulation two generating function whose coefficients exactly captures this part and this part. And I noticed that my generating function ax is just a product of bx times cx. And what is the advantage? It gives me an extremely closed form. This is like x by 1 minus x squared and x squared by 1 minus x cubed. So this is like x power 3 by 1 minus x squared. Now my life is very simple. So now I can find a closed expression for a. How do you find a closed expression for ax here? Just use your 10 plus 2 binomial expansion for negative exponent. Can somebody say what is the value of an? I have a value of an written here. My goal is to find it not this kind of summation form, but rather a nice form via a generating function approach. That's the illustration I'm trying to give. It's very simple, right? Because this you know by the identity, it is an x power n. That means you have to find the coefficient of x power n in this rational expression. How do you find the coefficient of x power n here? Already x cube is here. So it's enough to find the coefficient of x power n minus 3 in 1 minus x power minus 5. Right? Is there any doubt? Okay, so what is that coefficient? It is 5 plus 1. Let's use the binomial coefficient for negative exponent. So up to n minus 3, so we'll go to n minus 4 and then n minus 3 factorial. So that's the value of a. But what is that value? N plus 1 choose 4. That means your ax in its very nice closed form, which is just n plus 1 choose 4 x power. You may argue that by some other argument also I can understand this quantity is n plus 4 choose 1, for n plus 1 choose 4. True, this is a simple example, but there could be much complicated and harder examples where this kind of closed form will be hard to obtain unless you go via this analytic approach of finding a generating function. Yeah, I think it's already 6:30. So this is just one illustration that I could give the time that we have today. If you have any question, ask me. Otherwise, I will stop. You can stop recording though.